So today I want to show you a little experiment I've been working on, which I refer to as FractalWoman's Stern-Gerlach experiment. This is a Stern-Gerlach-like experiment where you have, so it is sort of analogous to this experiment where you have a North Pole and a South Pole, and you have something that is going in between, that you're sending in between the North and the South Pole. So in fact, this orientation kind of matches better with this orientation of these two magnets, where you have North up here and you have South down here, and here I have North up here and I have South down here. And in the Stern-Gerlach experiment, one of the magnets is configured to have a stronger magnetic field, and the other one is configured to have a weaker magnetic field. Okay, and so in this experiment, in my experiment, one of these magnets actually has a stronger magnetic field. I believe it is this one down here is an N52, and this one up here is an N42. Okay, so this is as close as I could get to simulating in a very simple way the Stern-Gerlach experiment, which I am depicting right here. Now what I'm showing here is we've got the North Pole here and we have a South Pole here. I'm also showing the potential isopotentials of these two magnets. Now the isopotentials aren't for to scale necessarily for these magnets, but this is just to show you how I am representing magnetic fields using magnetic isopotentials like I talked about in my previous video. So what I'm going to be doing in this experiment is I'm going to be taking some very small spherical magnets, small compared to the size of these magnets, and I'm going to be placing them in various locations relative to these two magnets, and we're going to see what happens to these small magnets. Now this is what I call a small magnet in the vicinity of a large magnet, and so we're going to place these magnets in between these two magnets, analogous to what they're doing in the Stern-Gerlach experiment. But before we do that, I want to talk a little bit about the language that I developed in my previous video, which I did on the comparing. So I'm still quite fascinated with the idea of comparing the isopotential diagrams from the magnetic field generated by magnetic field. So this is an alternate magnetic field diagram. It's a field diagram where every point in the field is assigned a value, and in this case it's a potential. And as I talked about in the previous video, these isopotentials are look very similar to, I was pointing out how they look very similar to the electron orbital diagrams from quantum mechanics. Okay, so the basis of quantum mechanics are these field diagrams. You can think of them as field diagrams. They are potential. They are generated using the potential component of the Schrodinger equation. So these are potential diagrams, and these are potential diagrams. And of course, I am fascinated by the similarity of both these diagrams to the sound fields radiated by a simple source. Okay, I showed you this before, how spherical harmonic oscillators interact with each other, and so you see that they tend to form field diagrams through their interference pattern that looks an awful lot like the field patterns that we see in both the isopotential diagrams and in the electron orbital diagrams. Okay, these are graphs, these are diagrams. These all three of these appear to be associated with something we call spherical harmonics. Okay, and so I find this very fascinating, and so I think this is something that we should explore a little further. And because of the self-similarity between these diagrams, I would like to try and coordinate a language, to try to unify a language. And so in the language of the electron orbitals, we have the concept of a node. Okay, so this electron orbital diagram here has a one planar mode. Okay, one planar node. And so a magnet, I am referring to this region here also as a node when talking about magnetic isopotentials. Okay, and so here we have a electron orbital diagram with two planar nodes, and here we have an isopotential diagram with a magnet of this configuration with two planar nodes. Okay, so I'm going to be referring to these as planar nodes. And I also want to show you something interesting. Here is the ferrocell diagram, or ferrocell image, picture, photograph of a magnet that is in this configuration. So it's actually in this configuration here where we have north, south, south, north. And when you put that under the ferrocell, you get a diagram that looks an awful lot like the electron orbital diagram, okay? And so there's lots of ways of looking at this, and this is what I love, the similarity, the self-similarity between all of these situations. And here is one more self-similarity that I would like to point out, kind of for fun, more for fun and more just to be thought-provoking. Okay, so here is the electron orbital for a where there is just one planar node, and here is an isopotential diagram with just one planar node. And this picture here in the middle is a picture of cell division. Okay, so this is an interesting idea because when you take a magnet and break it in half, what you end up with is, so when you take a magnet with one node and break it in half, what you end up is with two magnets, each with one node. Okay, and so of course when you do cell division, you take one cell and one cell divides in half to create two complete exact copies of the cell. So there is an interesting self-similarity between what happens when you break a magnet in half, like I showed here, and the concept of cell division. Okay, so there's a similarity between breaking a magnet in half and ending up with two magnets, and a cell dividing from one cell into two identical copies of the cell. Okay, so another thing to think about, more food for thought. And but that is not the point of this video. The point of this video is to have a look at this experiment and see what happens to a small magnet when you place it in the vicinity of two large magnets, or exactly in between the two large magnets. Okay, one more thing I want to say about the isopotentials themselves is what happens to these two magnets as you bring them closer together. So in the experiment I'm showing you, the magnets are kind of far apart. Okay, and so I want to show you just what happens to the isopotentials as you bring them closer and closer and closer together. Okay, so here they're far apart and they may or may not be interacting. As you bring them closer together, of course, these two fields start to interact. And in terms of harmonics, there would be some, in terms of a standing wave, there would be some destructive interference going on here because this is a north and this is a south. And so as you bring them closer together, first of all, I want you to see that there is a node forming here, potentially a node forming here, similar to these two nodes. So this is a north pole and a south pole. This is kind of like the Stern-Gerlach experiment in between a north pole and a south pole. This is what the isopotentials look like. And when you bring them closer together, they get a little more squished. Okay. And then as you bring them even closer together, they get even way more squished. And then finally, when the two are touching, they become as if they are one magnet. So you end up with one magnet, even though this used to be two magnets, it came together to form one magnet and with one node, okay? And so let's just have a look at I'm just going to show you the how you can see this under the magnetic viewing film. Okay, so here we have two magnets that I've separated with some distance. Okay, I put a spacer, excuse me, a non-ferrous spacer in between these two magnets. And when you look at the magnetic viewing film, okay, you kind of see this picture up here. So you see there's a node here, there's a node here, and there's a node here. There's a node here, here, there's a node here, and there's a node here. So you can see exactly by looking at this, and you've got this sort of black blobby region here corresponds to this region here, and this region here is this region here. This region here is this region here, and this region here is this region here. So you can see everything you need to see. There's a better view of it looking under the magnetic field viewer. Okay, so you can see that there is in fact a node forming here as you bring them closer and closer together. Okay, and then what I did was I brought them very close together, like in this situation. Okay, I brought them very close together, and so you'll see as we bring the magnetic viewing film, okay, you can see, let me just stop this here and get maybe the best image. Okay, you can see the, now it's a lot fainter, but you can still see the node in the middle. Okay, you can see the node in the middle. You can see it better maybe when I do it like this. So when I bring the film just slowly in, you can see there's still the node here, which is here. You've got this node up here. So you got sort of this region here is this region here. This region here is this region here. Okay, you've got the sort of black blobby region, which is up here, and this region down here is this region here. So you can see, even just looking under the magnetic viewing film, you can see this exact pattern. Okay, and so so the situation that I have in my experiment is more like this situation here, where the magnets are kind of far apart. I don't know how far the fields extend out, but they do appear to be coordinating with each other. And so the magnet, when I put a magnet in between, it can feel these two magnetic fields, okay, and it's interacting with them. And so it is likely more this situation that I'll be showing you in the experiments. Okay, so let's have a look at a couple of experiments I did using this kind of setup, and we'll just have a look and see what happens. So here is my first experimental setup. I have the two magnets relatively far apart because I want to kind of prevent this magnet from easily going flying to this magnet or to this magnet. And I've calibrated this. I've placed these two magnets so that this magnet here is perfectly balanced along this middle line here. Okay, so you'll see when I play this video, when I pick up the magnet and place it on the line, what it does is it oscillates back and forth. Okay, so it is oscillating back and forth along this line here, which is the node between these two magnets. Okay, let's do it one more time, and you'll see that it is moving back and forth, oscillating back and forth along the node, and it eventually settles exactly in the middle. Okay, exactly in the middle where the forces get balanced. Okay, so it stops in the middle where the forces are balanced, like we had right in the middle here. So let's have a look at the isopotential diagram to see if we can figure out what is going on in the animation. So here we have the isopotential for this magnet, and we have the isopotential for this magnet, and we have the isopotential for the small magnet. And what's happening here is the small magnet is moving, oscillating back and forth until it goes into this balanced situation right here. And so when the magnet, now first of all, I just want to point out that I'm not pushing the magnet. Okay, when I drop it, it automatically starts moving. I'm not forcing it to move or pushing it. These two magnets are creating that motion. And so what's happening is so this half of this magnet here is attracted to here, and this half of the magnet is attracted to here. And because the forces are balanced, it can't move this way and it can't move this way. And because it is a sphere, it can roll. And so what's happening, it is rolling, and it has enough force to go past the center point, and then it begins to roll this way, and then it begins to roll this way, and it oscillates back and forth until it ends up right in the middle. Okay, so that is what we are seeing when we look at this video here. We are seeing it oscillate back and forth. Okay, we're seeing it oscillate back and forth. Let me just do that again. Okay, it's oscillating back and forth until it gets to the middle. Okay, so here is my next experimental setup. I have the two magnets slightly closer to each other, and I just wanted to remind you, earlier I told you these two magnets were different strength, and so this is on the left here is the N52 magnet, and on the right is the N42 magnet. And so, and this line here is exactly physically in between these two magnets, okay? And so here what I'm doing is I'm placing the magnet on the center line. Let's have a look at that again. Okay, so I'm going to put it right on the center line. And as you can see, it starts on the center line, but then it oscillates back and forth. And it oscillates back and forth, okay, and then flies to the magnet on the left. And this is because the magnet on the left is a little bit stronger. So the center line is actually a little bit, is not the node of these two magnets between these two magnets, okay. It's a little bit off. And so the next one, what I'm doing is I'm placing the magnet. Let's just see if I can see that. I'm placing the magnet a little bit to the right of the line, okay? And so you will see that the magnet is oscillating back and forth, and it ends up stabilizing right a tiny bit to the right of these two magnets, okay? And so the node between these two magnets is here and not here, because this magnet is a little bit stronger, and this magnet is a little bit weaker. And so the point where all the forces balance is right here and along this line, but right here is where the forces balance between these two magnets. Okay, so here I want to show you what happens when you place the spherical magnet on the line or to the left of the line. It flies to the left. Okay, so if you put it on the line or to the left of the line, it flies to the left. And when you place it to the right of the line, it flies to the right. Okay. So there it goes, to the right. Now the right is the weaker magnet and the left is the stronger magnet. And so if you place it significantly to the right, it goes to the right. And if you place it significantly to the left, it goes to the left. Now in this case, it actually, let me just pause this here. It didn't fly to the right because, so one of the reasons it even just does this oscillation back and forth is because of the friction of the paper. Okay, if the paper wasn't here, or if the paper was infinitely, it had zero resistance or zero friction, then if I place a magnet here, it's going to fly to the left or to the right. And so if I place a magnet anywhere except in exactly the balance point, it's going to fly to the right or to the left. And so the friction of the paper is actually what is preventing this magnet from flying one way or the other. So there's a lot going on here. There's gravity pushing down on the spherical magnet, which creates a friction with the paper, and that prevents it from literally flying to one magnet or the other magnet. Okay, so that is a big difference between the Stern-Gerlach experiment and this experiment. This experiment, we have frictional forces that are, basically preventing this magnet from flying one way or another, but the similarities are that the magnet is going in between these two magnets, and sometimes, as you see, let me just quickly fast forward through it. Sometimes the magnet goes to the left, and sometimes the magnet goes to the right. It really depends on where you place it in relative to these two magnets and relative to the node between these two magnets. So when looking at this in terms of the isopotential diagrams, what we have here is a small dipole moment with a node in the vicinity of two larger dipole moments, each with their own node, and with a node actually forming in between these two. Okay, in between these two, and actually it is kind of more like the situation here. Okay, so here we have a small dipole moment with its own isopotentials and its own node. And so what happens is, if the node of the small magnet finds itself a little bit to the left of the node of the two big magnets, it flies this way. And if the node of the small magnet finds itself a little bit to the right, even just a tiny bit to the right, okay, it's going to start moving like this, and then it's going to eventually fly to this magnet. Okay, so that's what we're seeing in my experiment. We're seeing if the forces are balanced, then it's just going to go back and forth like this, and it's not going to fly to one magnet or the another. But if it's a little bit, if you place it a little bit to the left of the node, it's going to kind of go curved like that and then fly to this magnet. And if it's a little bit to the right of the node, it's going to kind of curve like this and eventually fly to this magnet. Okay, so that is what we are seeing in the experiment that I just showed you. And so this is the isopotential diagram. Now we have to take into consideration that the dipole moment here, it also has an isopotential and also has a node. And so we can talk about everything in terms of nodes. And so if the node of this is to the left, it flies to the left of the node of the big setup here. It flies to the left. And if the node of this small dipole moment finds itself to the right of the node of these two magnets, then it's going to fly to the right. So that is the essence of the Fractal Woman Stern-Gerlach experiment. Now, how this relates to the actual Stern-Gerlach experiment remains to be seen. Okay, so how this relates to this experiment remains to be seen. This is an experiment that anyone can do. Anyone could buy two magnets and buy those spherical magnets and play around with the behavior of what happens in between these two magnets. Okay, so I just wanted to get this out there. I've been working on this for a while, and so I really just wanted to get as much out there as I could, and then you can have a look at it and we can discuss it further. And if you have any comments about this, any questions, please leave a comment in the comment section. All right, so have a good day, and I'll be back.